Hello, I'm Hayley Fowler from the School of Engineering at Newcastle University, and I'm going to be talking today about linking climate and weather to hazards and risks, hydrological extremes. So the idea behind this talk is really trying to link the information we've heard from the previous talks on the climate science that we understand in terms of projected changes through to the impacts that we'll hear about in the next panel. So I'd like to start really by the 6 priority areas that were identified in the Climate Change Risk Assessment 2, where more action was needed as a priority moving forwards. And 2 of those, as you can see by the red highlighted areas, are really around hydrological risks. One of those is around flooding, coastal changes, risks to communities, business and infrastructure. And the other one really is on the other end of the spectrum, and that's thinking about the shortages in potential public water supplies and the knock-on impacts on, therefore, agriculture, energy generation and industry. What I'm not going to talk about today is the highlighted orange boxes, where these are sort of knock-on effects from risks to water. So they're connected, but they're not actual hydrological risks. And when I'm talking about risk, and I know that Nigel's already introduced this concept, risk is defined here as a hazard, which might be an extreme weather event, for example, times the exposure, which is the exposure of that particular person or community or building to the event, so perhaps a flood depth, and that would be multiplied by the vulnerability, and that's the vulnerability of that particular person to flooding. So it might be that the person is, say, old or incapable of moving, disabled or something, and therefore you've got some vulnerability criteria as well. So it's not enough just to be thinking of risk as hazard, which is really what the information we get from climate science. However, to start with in this talk, I am going to be talking about changes to hazards, and in particular extreme rainfall that we've produced in our research. So what do we know already about changes to hydrological hazards and risks? Well, what we know is, and what was suggested by Kevin Trenberth in a landmark paper that he published a long time ago now in 2003, is that we expect extreme precipitation intensities to increase with temperature at approximately the Clausius-Clapeyron rate. And this is a rate of about 7% per degree of warming. And the Clausius-Clapeyron relationship basically says that as the temperature, air temperature increases, then the saturation vapor pressure of air also increases. And because extreme rainfall occurs at approximately saturation, when air is saturated, then we'd also expect these extreme precipitation intensities to follow this relationship. And what Kevin also said in his paper, though, is that because of the energy constraints on evaporation, because evaporation cannot occur at that same rate, then we would expect that the mean precipitation or the total precipitation will increase at a much slower rate. And actually, the expectation in terms of that rate is something around 2 or 3%. So it's quite a lot lower than what we'd expect for the 7% for extremes. And that also means that these intensity increases in the extremes must also be offset by duration and frequency changes. And in particular, that gives us this kind of almost irony of climate change, where we get more intense rainfall at the heavy end of the extremes, but much longer and more frequent dry periods as well associated with that. So we can actually have more floods and more droughts happening at the same time. And so we can get what we see here. And you can see on the left there is a convective thunderstorm that's happening somewhere over Canada. And we're expecting climate change to cause more of these heavy rainstorm events, and therefore more of these events that you can see in the middle there in terms of flooding. And what you can see on the right there is the dramatic reduction in water in the reservoir that serves Chennai in India. And at the bottom there, that picture of people queuing up, waiting for water from standpipes. And also on the top picture in the middle there, the navigation issues faced in Europe a couple of years ago by the severe drought in Central Europe. So we're expecting more heavy rainstorms and flooding, as well as heat waves and droughts moving forwards. And what we know so far in terms of this expectation of change in heavy rainfall from studies that have been done is that increases in the frequency and the intensity of daily heavy precipitation and longer durations is consistent with Clausius-Clapeyron scaling. And there was a paper published by Eric Fisher and Rito Nutti in Nature Climate Change in 2016. And you can see that figure on the left there. And they looked at the change in the frequency of different percentiles of daily precipitation. And you can see the grey shaded area there shows a resampled range. And they looked at observations for 2 different time periods and then looked at the change in the different percentiles between those 2 time periods, and then also assessed how those were related, the dotted blue line, to this Clausius-Clapeyron scaling relationship. And what you can see is that the change in the daily precipitation percentiles between the 2 time periods is consistent with what we'd expect from Clausius-Clapeyron. That's for daily precipitation. What you can see on the right is some work that was published by Selma Guerrero in Nature Climate Change in 2018, using the same approach to look at the changes in intensity between 2 different time periods for daily and hourly rainfall extremes. And again, it's a very similar approach. Rather than saying, looking at percentiles, now looking at these K largest bins, where, for example, the 20 largest bin would be the 20 largest events in each time period. So looking at the difference in intensity between the 20 largest events between the 2 time periods. And the same with between 40 and 20, for example, you need to look at the next highest 20 events. And what we found was that for daily changes, these were consistent with Clausius-Clapeyron. And you can see that bottom red dashed line there is the Clausius-Clapeyron relationship. And the blue line is what the changes we found. And again, the grey shaded area shows this resampling range. So the changes are consistent with Clausius-Clapeyron, but also within the range of natural variability for daily heavy rainfall extremes. For hourly, however, the change, this blue line here, is consistent with a much higher rate. So it's outside the range of natural variability, but it's also consistent with a rate from about 1.5 to 2 times Clausius-Clapeyron scaling. So what we know is that these increases in hourly rainfall intensities can be much higher. And this isn't necessarily consistent across the world, but there is that potential to get much higher changes in these hourly rainfall extremes. What we also know from research that's been done around the world is that we're also expecting changes to the temporal profiles of storms. And this was a nice study done by Conrad Wasco and Ashish Sharma in 2015, Nature Geoscience, who looked at parts of storms. Basically, they split up storms into the more intense and the less intense time periods, and then looked at how those related to temperature. And they found that you get more intense peak precipitation and weaker precipitation during less intense times at higher temperatures. And this was regardless of the climatic region and season across Australia. So we can perhaps expect storms to become more intense in their peak, but perhaps shorter or weaker during that less intense start and finish. The other thing is we can expect changes to storm size as well as this peak intensity with global warming. And there have been a few studies on this now. And there have been a couple of studies on observations from Australia and the Netherlands. And actually, although they used the reversed colours in their figures, and you can see this on the left and in the centre there from Wasco and Lochbihler, they actually find similar results in terms of increases in the peak intensity of this central part of the storm with warmer temperatures. And you can see that there in Australia with the red line with increasing peak intensities, and in the Netherlands with the blue line, increasing peak intensities in the storm. What is different, however, is in Australia, with warmer temperatures, we tend to get smaller storms. So they become more intense, but smaller. Whereas in the Netherlands, you get more intense storms and they become bigger. So the total rainfall increases. And actually, that's what Andy Prine found from a convection permitting model simulation over the USA for the end of the century. And he found actually that you get an increase in the peak of the storm, peak intensity of the storm, but also an increase in the size as well. We found similar results over the UK as well with our convection permitting model results. The implication of this is actually it's important to look at the total event rainfall when we're trying to understand risk, including the duration and the spatial extent of storms, as well as these peak intensities, to understand changing flood risk. At the moment, most of our flood risk estimation methods are based on these peak intensity estimates. And we really need to start thinking in different ways if we're to understand and to plan for changing flood risk in the future. So of course, this change in rainfall intensities will cause changes to flood hazard, which will vary regionally and by catchment. And I think there's some interesting things to think about here with changes to seasonality. You can see on the left here from a paper published in Nature Climate Change, looking at decadal changes in precipitation for Sydney in Australia. And you can see that they looked at the change per decade in different storm burst durations from 5 minutes up to 48 hours for different seasons. And when you think about our current flood estimation methods, we base them on the annual maxima. And when you look at those, you can see that the 5-minute annual maxima are increasing, but actually once you get to about 3 hours, they're decreasing. There's a significant decrease in these annual maxima. But actually, if you look at individual seasons, you can see that actually in some seasons you're seeing increases across the whole of this storm burst duration range in summer, for example, whereas in other seasons in winter, you're seeing decreases across the whole of this storm burst duration range. And actually this change, seasonal change, has implications for flood risk management as well, because using this annual change may not be may underestimate, I suppose, the potential changes in flood risk. And also because different types of systems produce different types of flood risk, the difference between, for example, surface water flooding and fluvial flooding from rivers, then we really need to be considering these different changes in different seasons. The other thing to say is that actually, although rainfall intensities tend to increase with temperature, as we've already seen from this Clausius-Clapeyron scaling, actually, when we look at stream flow extremes, they actually tend to, on the whole, decrease with temperature. And of course, that's because of the impact of evapotranspiration in the catchment on antecedent conditions. And therefore, as temperatures increase, you get an increase in evapotranspiration, and therefore the moisture and antecedent conditions become drier. And therefore, an increase in extreme rainfall will not necessarily cause an increase in flooding. And the implication of this, though, is that small subcatchments may exhibit very different flood trend magnitudes or even direction to larger catchments, since smaller subcatchments are potentially less affected by these antecedent moisture conditions and much more affected by the potential changes which may be larger to these very intense short duration convective storms. And there's been some work done in preparation for the third UK climate change risk assessment, looking at the potential influence of climate change and other influences such as population growth and adaptation measures on UK flood risk for a 2 and 4 degree rise in global mean surface temperature by Paul Sayers and partners. And they found that the influence of climate change was by far the greatest of the things they looked at. So therefore the hazard, if you like, provides the biggest part of that risk. The changing hazard provides the biggest part of that risk. I mean, what I will say, and what I'll say in a moment as well, really, is a lot of the problem with these risk assessments at the moment, I think, is that we're using highly sophisticated climate science and then translating that through into our risk models or our impacts models in quite crude ways, in quite simple ways. And we're also not taking account of those other factors adequately in terms of the vulnerability and exposure within our risk assessments. So there's two things to think about there as well moving forward. So where are the key knowledge gaps? And there are many more of these which we can discuss at the panel, but these are some ones that I've pulled out to think about now. So there are still a number of things that we don't understand about the potential changes to heavy rainfall, which is a large driver, obviously, of changes to flood risk, and that produces that hazard. And you can see here, the top diagram really shows the processes we understand in terms of how those will change. We'll get stronger storms, stronger updrafts, and deeper convection in the future. But there's a whole load of processes there that we don't understand well enough as well. And you can see at the bottom there as well some missing pieces. And one of the largest of those really is thinking about the influence of changes to large-scale circulation dynamics. And I think this is where climate science is still crucial. We really need to understand what might happen to those large-scale dynamics to understand what might happen to flood risk in the future. The other things we really need to be thinking about are changes to storm characteristics and all sorts of other things that cause big feedback effects in storms. The other thing we need to think about is, and we don't understand well enough at the moment, is where and when does increasing extreme rainfall cause increasing flood hazard? And you can see on the left there by Gunter Bloschel et al. In Nature in 2019, observed regional trends of river flood discharges in Europe. And you can see that actually we're seeing increases from 1960 to 2010 in Northern Europe, but decreases in the Mediterranean and in Eastern Europe as well. And that relates to some of the things that you can see over on the right there, where Ashish Sharma and co-authors published a paper in 2018, really thinking about the relationship between extreme rainfall and flood hazard. And they came to some conclusions from the evidence in the literature that the rarer a flood is, the more it potentially will increase. That discharge increase will be potentially more for smaller catchments, and that's for the reasons we've talked about. I've just talked about previously. Although precipitation has this positive sensitivity with temperature, flooding does not necessarily, but it does in smaller catchments, and therefore we expect an increase in urban flood risk, but not necessarily at these larger scales in terms of fluvial flooding. So we can get the case where precipitation increases while flow decreases. And this is important, moving on to the next gap. But I think that part of the issue here is that we're using hydrological models for our impacts that are insufficient in terms of simulating the processes that we need to simulate to understand potential changes to flood risk. A lot of the models we use at the moment are very simple and conceptual in nature, and it would be useful to think about the benefits of using some of the models that are more commonly used in academia within our, whether it's flood forecasting or whether it's flood risk management, using physically based models, which are hopefully more predictive because they're based on physical processes rather than statistical relationships. And therefore things like SheTran, or potentially things like hydrojoules, which would then obviously connect this up to climate modelling, and you might be able to actually have a full system of climate and hydrology connected up rather than using offline hydrological models. The other thing at the moment is that, as I said previously, we use quite simple methods to translate our climate science through to impacts, and particularly when we're thinking about hydrological impacts, we apply simple climate uplifts, which we've got from flow response surfaces through things like future flows. We don't think about the sequencing and clustering of rainfall, which is very important for flooding, as well as the antecedent conditions. And certainly these delta change methods that we use at the moment are not sufficient. And we need to be thinking more clearly about how we take information from these sophisticated climate models that we now have, rather than using simple delta change from our probabilistic projections, for example. How do we bring together information from all of the different strands of UK CP18 in the most intelligent way? And how do we better incorporate information on exposure and vulnerability? So the final gap that I think we need to address is really thinking about compound risks and hotspots. And when I was thinking about the changing processes that cause surface water flash flooding, you can see a nice diagram there that Richard Allen put together for a review that we have in press in Nature Reviews. And there's a lot of feedback effects really causing surface water flash flooding. But the other thing that we need to think about within that is increased compound flooding from intense rainfall and storm surges, from fluvial flooding as well. And in particular, thinking about these compound risks from concurrent or successive extreme events and from interacting risks. I'm not going to talk about cascading risks here or interconnected risks because I think they'll be covered adequately in the next presentations. So what are the opportunities for progress here? I think that one key opportunity at the moment is using new data sets to understand current climate variability better to improve flood risk estimation. And one of the ways we've tried to do this in the UK is using high resolution gauge radar satellite data. We don't understand at the moment how often extreme events occur or their spatial characteristics, and therefore we can't plan for the risk associated with those events. So producing blended gauge radar satellite data sets really helps us to understand the spatial aspects of these extremes that we need to understand for flood risk management. The other thing we need to do is seriously think about revising the current flood estimation methods that we use in the UK and elsewhere. At the moment, we use industry standard statistical models to estimate extreme variables, but we don't routinely account for non-stationarity in the current climate. And we really need to be doing this to make decent estimates of how that hazard and risk will change in the future. And part of this is also thinking about how do we include those changing storm characteristics that we've identified in the science? How do we include changing seasonality? How do we include changing intermittency and clustering of storms into our flood risk estimation methods? How do we actually include things like the changes to the temporal profile of storms? Do we need to use new storm profiles that represent these things? Do we need to change those in new ways to actually account for those changes that we've quantified from models? And I think there's a real opportunity here to use these convection permitting models to tell us about changes to seasonality, changes to peak intensities, changes to those characteristics of storms that really matter, and to then incorporate that information into our flood risk estimation and management methods. The other thing we really need to be thinking about doing is how do we make climate change risks and risk information more relevant for decision makers? One of the ways of doing this, I think, has been really well shown by some work we've done with Murray Dale, led by Murray Dale in 2017, and with UK water industry research and working with the UK water companies to come up with climate uplifts for urban drainage design. But to do this, we need to be thinking about how do we link actions to outcomes. To achieve something, we need to know Y and Z. So we need to know what do we need to know? What do they need to know? And who will benefit? And how can we best use climate change information in decision frameworks? And that has to be done together with decision makers. So it's not enough to just produce the best climate science. We now need to be thinking about how do we actually use that climate science? And not only that, but how do we design climate science to achieve what we need to know? The final thing I wanted to talk about today was really using our new process understanding and expert judgment to produce storylines of plausible extreme events for risk assessment. I think this is a really exciting area and somewhere that we really have an opportunity, rather than simply using time series information from global climate models or regional climate models, rather than simply using probabilistic scenarios and projections as we've produced in UKCP 18, we have the opportunity really to produce storylines of a past event, but something that can be adapted to produce something that decision makers would understand as based on a past event, but perhaps interpreting that event in a slightly different way, saying how it might change in the future, so that people can then use this information to plan adaptation measures. And I think there's some really good examples in the literature now about how these storylines can be used to plan and manage crisis situations and to allow the testing of these management strategies during crisis situations. So I would hope that we can start to move towards designing these type of storylines together with decision makers. I mean, I think to summarize, I think that what's crucial now as we think about what we actually need to know about in terms of impacts, what we need to know about in terms of adaptation decisions, and then feed that backwards actually to the climate science. Climate science can provide brilliant answers. It can provide models that can now reproduce even convective extreme rainfall events very well, and good projections of what might happen in the future, but it can only tell us what we ask of it, and we need to know what we don't understand and what we need to know first to then design some co-design experiments or simulations with climate science and decision makers' involvement to actually really think about how do we move forward with adaptation